All right, welcome to the notes on 3-4. This is we're going to talk about direct variation today. It's a very specific kind of linear equation, and typically it's one that we can understand pretty well because it comes up a lot in real-world situations. Okay, a direct variation is described by an equation of the form y equals kx. Now, why they use k and not m, I'm not sure, but this k right here is m. It's just like slope. Okay, that is the slope. And k can equal 0. Now, I kind of just kidding. I do know why they used k, but it's because it's the constant rate of change, and constant starts with a k sound, so there's your k. It's often referred to as the constant of variation or the constant of proportionality, and more typically, I think you'll see the term constant of variation. So it's just the slope, okay? So when it says name the constant of variation, we should see this right here where it says constant of variation, and we should just be thinking, all right, they're just asking me the slope of that line, okay? So they tell us in the problem that the slope is -4. So very simply, the slope is -4, okay? And yeah, so this is that, okay? And again here, y equals 1/2 x. The slope is 1/2, so the k is 1/2, okay? Name the constant of variation for y equals 1/4, okay? So they want us to name the constant of variation for y equals 1/4. Well, the constant of variation here, we would say k equals, and it's just that 1/4. That's all it is. Then find the slope of the line that passes through the points 0, 0, and 4, 1. So if we were to graph that, we would have 0, 0, and 4, 1 would be right there. 1, 2, 3, 4, and then 1. Well, if we were to look at the rise over run of that, okay, the rise over run would be up 1, up 1, and then over 4. Let's do that. Up 1, and then 1, 2, 3, 4. And so the slope of that line would be 1/4. Name the constant of variation here. Okay, so again, constant of variation is just this number right next to the x, so the k equals -2. And then let's take a look here. Find the slope of the line that passes through the point 0, 0. So again, we have 0, 0, and 1, -2. And the rise over run there would be down 2 over 1, which the slope there would be -2. The slope of the graph y equals kx is k. So this is where they're getting to the point. K and the slope are the same thing. Since 0 equals k times 0, the graph of y equals kx always passes through the origin. Therefore, the x and y intercepts are always 0. This is like a big key, okay, for direct variations. They always have to go through the origin. Always, okay? But make sure I wrote that down. All right, let's take a look here. So if we were to graph y equals -6x, the easiest way to do this is to just go into your graph. You put a point at 0, 0, and then you use -6. Use this slope here to find the next point. So it's down 6 over 1. Boom. There's the second point, and that's how I get my line. Okay. You don't need graph paper. Okay. You don't need graph paper, but if you could, please go ahead and sketch 2A, 2B, 2C, and 2D. Just give me a sketch of what those would look like. Go ahead and pause the video now and sketch those graphs. All right, so let's take a look and see if your graphs match mine. Here's what I got. You'll notice each time I have a point at the origin, and then I use the slope to find the next point. So up 2 over 3, down 5 over 1, down 3 over 4. So there's my 4 lines. Okay, direct variation always goes through the origin. All right. Let's take a look here. Oop, too far. So again, the graphs of all direct variations share some common characteristics. The common characteristics are they're in the form y equals kx. Okay, so they all should look like this. It always passes through the origin, so that's important. If the slope is positive, k is greater than 0. And if the slope is negative, k is less than 0. So real simple stuff. In a relationship between the values of y and x, if they're described as a direct variation, then we use this terminology right here. And this is important to understand because you're going to see this in questions. So you need to know. We say that y varies directly as x. This is like a giveaway. It's a hint, not a hignant, a hint that we have a direct variation. Okay? So this is a hint that we have a direct variation. It's how the problem tells you that's what we have. So questions like this exist. Suppose that y varies directly as x. All right, jumped again. And y is 72 and x is 8. So first it says write a direct variation that relates x and y. So we find the k, and then we just plug it in. Then it says use the direct variation to find x when y is this. Well, then we just plug the y in and we solve. Very simple stuff. Okay, I'm going to walk you through how to do one of these. So it says suppose that y varies directly as x, and x is 98 when y is 98 when x is 14. So this is the equation. They're telling us that y is 98. We don't know k. X is 14. Okay? If we divide both sides by 14, we get k equals 7. So then our direct variation equation is y equals 7x. Then it says, so that's part 1. Part 2, find y when x is negative 4. So y we don't know. 7 is there. X is negative 4. So y is 28 when x is negative 4. And that's it. Let's take a look here. One of the most common applications of direct variation is the formula distance equals rate times time. You'll recall that from the last test. The distance a jet travels varies directly as the number of hours it flies. So a jet travels 3,420 miles in 6 hours. So we're able to figure out the rate. Okay. Then we can graph it very simply, and we can estimate all sorts of things based on that graph. Okay. So let's look at here. We have a hot air balloon height, and it says it varies directly as the balloon's ascent time in minutes. So the height and the time vary directly. Write a direct variation for the distance d ascended in t time. Okay, so, excuse this interruption. So if it goes 350 feet in 5 minutes, that's 350 feet in 5 minutes. The constant of variation there is 70. So part A, y equals 70x. Graph the equation. All right, graph, and actually, let's do this, because we're not going to go negative feet or negative time. Sorry about that. Let's just graph it here. And so say we have, we'll go minutes. We'll go 5, 10. This doesn't have to be a lot, and it doesn't have to be perfect. 5, 10, 15, and we'll go here. We'll say this is 50, 100, 150, 200. So in 5 minutes, and actually, whoa, sorry, I need to make my numbers way bigger. Okay, let's just say 100, 200. 300 and 400. Okay, so in 5 minutes we went 350, so that's here. 10 minutes we will have gone 700. I need to make my graph way taller, so 5, 6, 700 up here. How far would I have gone in 0 minutes? And the answer to that is 0. That's the height. Okay, so that's how we get that. And then we can draw our line. Yikes. Our line going through the origin. So there's part B. There's our graph. Estimate how many minutes it would take you to ascend 2,100 feet. So 2,100 equals 70x. Okay. So how long would that take? It looks like it would take about 30 minutes. Exactly 30 minutes. How many minutes would it take to ascend 3,500 feet? So 3,500 equals 70x. Looks like that would take about 50 minutes. Okay, very easy to see this in some real-world problems, all right? What I'd like for you to do is, and I really would like for you to do this, I would like for you to try some of these problems here from 1 through 9, okay? Give these a try and then come with questions. I think that the questions really should come mostly from 7 and 8. These are the ones where the algebra is involved. The rest of them will probably be pretty good at, but give them a try. And come to class with questions, and we'll see what we can do. See you guys next time. Don't forget, quiz on 3-1 through 3-3 next time. Bye.